So this is for the post lab, the vitamin C post lab. The average volume of sodium hydroxide in liters, we ended up using around 20 milliliters worth. And if you do the for every statement where 1,000 milliliters are 1 liter, what you end up with is 0.02 as your liters. In trying to figure out the molarity of the sodium hydroxide, what we did was we took 0.1 molar solution, we took 0.015 liters of it, and we added water up to 150 milliliters, or 0.15 of it. So this was our first solution, and we took water, 135 milliliters, or 0.135 liters, and we created a new solution. This new solution is 0.15 liters, and we're trying to figure out what the molarity of this is. So if we can figure out the number of moles we ended up using when we did this stuff here, well, that's the number of moles that is going to be in this stuff there, we can figure out the molarity. So for every 0.1 mole of NaOH, there are 1 liter, and we know that because we started with 0.1 molar solution. So we didn't have 1 liter, however, we had 0.015 liters. So if we're multiplying by 0.015, we're multiplying by 0.015, we should end up getting 0.0015 moles for that 0.015 liter. And this mole, 0.0015, is in there. So now we have a new for every statement. For every 0.0015 moles, there are 0.15 liters, and we're trying to figure out the molarity, which is always in 1 liter. So in that case, we're multiplying by around 6.7. If we multiply by 6.7, we should get as the molarity 0.01 moles. So this molarity of the diluted is 0.01. For the next one, in trying to figure out the moles of sodium hydroxide, you're going to have to use the molarity which you got from the previous one, and you're going to use the amount that you ended up using. So if the average volume we used was 0.02 and the molarity was 0.01, so we can do for every 0.01 moles, there are 1 liter. But we didn't use 0.1 or 1 liters worth. We used 0.02. So 0.02 times 0.02 times 0.02. And what we should get for the total number of moles is 0.0002. As the number of moles there are. So that's how many moles we've got on average for that. For the next part, in figuring out the moles of ascorbic acid, that's what vitamin C is, and we know that we were working with 500 milligrams converted to grams, it's going to end up being 0.5 grams of that acid. The formula weight for this is 176 grams for every 1 mole. So in trying to figure out the number of moles that we're getting from that, we should get 0.003, and I rounded there. It's actually 0.0028 something or another. So that's the number of moles you've got. The average volume of it. So once again, I'm giving you my numbers. We're going by 0.02 liters. And then the molarity of the ascorbic acid. So you've got moles, you've got liters, you're trying to figure out molarity. So for every 0.003 moles, there are 0.02 liters. You're trying to convert that to 1 liter, and you're trying to convert that, and whatever you end up getting, you should get somewhere around 0.15 as the molarity. For number 2, in a strong acid, the molarity is equal to the concentration of H3O+. If the ascorbic acid is a strong acid, what would the pH be? So what we found was that the molarity of the ascorbic acid was 0.15. So if we're going to assume that it's a strong acid, then that's going to be the molarity of the H3O+. The way you can write out 0.15 in scientific notation is 1.5 times 10 to the power of -1. So if we're taking the negative log of this number right here, we can assume that it's going to be somewhere around a pH of 1. When you actually calculate it, it should be around 0.82. For number 3, they give you a Ka value for ascorbic acid. And then it says if ascorbic acid is strong acid, it should probably be, actually written, weak acid. What would the pH be? So now we have to actually do a reaction. So let's say the ascorbic acid, which is H parentheses C6H7O6 plus water. So you have to remember that we have to write our own reaction because now we're trying to calculate the pH of it. We're not going based off the reaction that's at the top of the page. So if it's reacting with water, so that plus water would give you H3O plus that anion, which is C6H7, whatever it is. So the Ka would be basically the concentration of H3O+ times the concentration of the anion, C6 ... divided by the concentration of H, C6 ... And what we're saying is this right here is 0.15 molarity. So we have to figure out an ice table actually. So let's go ahead and do that right now. So what we're saying is the initial 0.15 molarity, because these are both products, 0 and 0. This is minus x, this is plus x plus x. What we end up having is 0.15 minus x, and then we got x over here and x over here. Now this we have to look at and see if we can forget about this minus x, and the way we'll know is if this Ka value right here is super small, almost 1,000th place smaller than the number you're subtracting x from. And in this case it is, because 7.9 times 10 to the -5 is a lot smaller than 0.15, so it doesn't really matter. So let's go ahead and plug in just the 0.15 and the x into our Ka. What we'll have is 7.9 times 10 to the power of -5 is equal to x squared. It would be x times x. I'm just doing one step ahead. And then it's just going to be 0.15 there. And then x is the concentration of H3O+, and x should be equal to 0.00344. Another way of saying that is 3.4 times 10 to the power of -3. pH is going to be somewhere around 3-ish. When we actually calculate it, it's 2.4. So that's the practice for tonight.